Hello and welcome back to another episode of the Oxford MAT Livestream. My name's James and today it's sequences and series. Some content that last week we said maybe not everybody has seen before, so we might be learning something new today. Before we jump in, I want to remind people that test registration is now open as of the time of recording, time of going live. You can register for the test, the sequences that you need to start a UCAS application, and then you can start a test registration. Booking is going to open 18th of August. In between streams, I will be giving people reminders that registration and booking is open once that's true. Right, let's see how they're doing over in chat. They're joining in as well. Let's have a look. Hello to Jacob's here. Good afternoon, Jacob. And already a question: is there logic, such as, and their example of logic is question 6, which, I mean, logic is allowed to be in questions. It's just you're expected to be able to do logical reasoning, I'm afraid. Whether that's in the form of, in question. There are some question 6 past MAT questions which had all this truth and lie stuff in and other stuff. Are you going to teach us all the series stuff if I haven't done any of it? That is very much the plan. I want to be useful, so I want to do things that might be useful to you. I have, of course, made some revision notes in advance. You can see them behind me on screen. Let's hide chat for a moment so that people can get a good look. We've got the MAT syllabus at the top and we've got some revision notes. If you want a copy of this, because my copy keeps scrolling up and down on a whim to show you, I'm going to show you things. If you want a copy of this, you can get a copy at the MAT Live page, which is on this website, which is on screen, or in the YouTube description. You can find it in other places as well. Hello to Rosie and Anonymous and Kay. Anonymous wants to know if most people have learnt this so far, which is tricky as a question. What I'll say is that some people, if you're doing A-level maths and further maths one after the other, if you're doing maths and further maths in parallel, then you might not have seen all of A-level maths yet, which might be one reason that this stuff is stuff that you're about to learn when you get back after the holidays. At the time of going live is currently the holidays, but you might not have seen it yet, so don't panic. We're going to have a look. There's only about 4 things that I really want to show you, and then we'll try some questions. But first, let's do the How's Your Day poll, which is currently looking like that for How's Your Day, and good evening to Neat. I'm having a good day because somebody who sadly is leaving, but unsadly popped by the office to say goodbye and to give us, to have it in our office, this. It is a triangular torus, a sort of donut shape, but made out of flat faces. And the point of making it out of flat faces is that makes it a source of polyhedra, and you could do things like counting the edges and counting the corners and counting the faces, and then you'll have a real surprise because you'll discover that it doesn't do the same Euler formula thing that other polyhedra do. So that's really great. There was Naomi. I can't remember if we've had Naomi on the live stream this year or maybe last year. For Maths Club is what I'm thinking of. Can't remember. Anyway, Naomi made this for a thing and has now donated it to our office so that it can join the vast array of other bits and pieces that we've got in the office. Good times. Anonymous asks, can you bring a pen and paper? And I'm afraid the answer is no. They give you a pen and whiteboard paper, which is note boards, I think they're calling it. They give you something to write with and something to write on. You can't bring your own stuff into the test centre, I'm afraid. Jacob says, when checking the values of x, why is it mod x has 1 instead of x between -1 and 1? I think those are the same thing. We can talk about it, Jacob. I think the 2 things in Jacob's chat message behind this poll are the same. A hasn't done this yet. Yeah, okay, good. There's a specific question with question 9. And good question from the chat at the moment. Sorry, just keeping up with chat while they're voting. They're having a good day, aren't they? Well, not everyone, but I'm always looking at the 1-star, the 2-star person, the 3-star person. But maybe learning some sequences and series would be fun. There was a good question there, which are there international test centres? To which the answer is yes, of course there are. One of the things about the MAT is that there are test centres all the way around the world, so people do it. More people are voting 1 and 3 stars. That's quite sad. Yeah, myself with examples. Depends. If the question says give us an example of something, then go for it. If the question says prove this in general, then the idea is that you prove it in general. Often if you're looking at solutions for the MAT live stream, this is a question from Kay about doing things in general versus doing particular examples. Often the thing that we've written to try and be helpful is as general as possible to give you the main things. Apparently people are having trouble with TMUA, so you can shared experience in chat. It's nice sometimes the chat does that. Chat's having a 3.9 star day. It started well, but it's not as strong as I thought it might have been. Possibly related to trouble with TMUA. And the question there, do you get unlimited whiteboard paper? Unlimited is a large number. You can request more. I guess that's limited by time, but not by the finiteness of the universe. There's a system where you can request more. They'll explain it to you in the test centre, if not before. So you might get some, and then they'll system to give you more. It is erasable. The idea is that it's erasable by the people in the test centre, not by you. You're not supposed to be ripping things out. Sorry, by the way, if you can hear loads of thunder and lightning going on. That is, I think, outside of my control. That is just what the weather is doing right there in Oxford. A bit scary. Right. What else are we doing? Ginger Biscuit has a joke about a Taurus that I'm not sure I understand. And Arnav at the top is preparing for TMUA. Starting MAT now. No, if you've been preparing for TMUA, then you've probably been preparing for MAT as well, because both of those things involve practicing tricky maths questions and similar content. TMUA is literally being booked right now by someone. There you go. Good. Okay. I would not hold your breath on 2024 MAT multiple choice questions. If you look at the past paper, you'll see that it says they're not being released. I wouldn't expect that to change before anytime soon. Okay, cool. Right. Okay, let's hide chat and let's learn some stuff about sequences. We're not having a great day. We're having an okay day. Right, here we go. So, MAT syllabus at the top is stuff that we're supposed to know. So this is what we're going to revise or possibly learn over the next, should we say, 15 minutes? I'll try and keep it pacey. Let's try and do this. So sequences defined iteratively and by formulae, which is the same as formulas, I suppose. Arithmetic and geometric progressions, so we'll see examples of both of those and a definition of each. Their sums, there's a formula for adding these things up, and the convergence condition for an infinite geometric progression, which doesn't mean anything unless you know what the geometric progressions are, and we will learn what that is in a minute's time. Here we go then. So first bullet point is supposed to be addressing, in the revision notes, is supposed to be addressing this idea that sequences might be defined with a formula. Like you might be told that an is n squared minus n, which is a bit like having a function, right? You put in the number n, you get the nth term of the sequence. So if you want a3, you plug in 3 into that formula. That's what this n squared minus n is supposed to be an example of. You might just be told with a formula what the nth term is. But it might be defined in terms of previous things. So maybe just in terms of the previous term, like that. A function where instead of just plugging in n, you plug in an, the previous term of the sequence, to get, in this case they would define an plus 1 as a function f of an. So this might be something where each term depends on what was going on before. That's quite good for mathematical modelling because, well, quite often you have things in the real world which depend not just on time, but on the previous condition that they were in. Mathematical modelling is not on the MAT syllabus. It's not an applied test. So in chat, the Fibonacci numbers are often given to you. If you've seen Fibonacci numbers, often given to you as a definition where it tells you about the sum of the previous two terms. The Fibonacci numbers start 1, 1, and then each term is the sum of the previous two. That's an example of some iteration, where each one, if you want the 10th one, you need, well in that case, that Ruben, in that case that chat's talking about, you need the 9th and the 8th. So you need the previous things. There is also a formula for Fibonacci numbers called Binet's formula. You don't need to know what that is. Just a little joke. I mean, in some sense, the fact that they're defined means that, well, never mind. Whether or not the formula is something that you can quickly calculate is sort of almost a philosophical distinction between, if you need the 10th Fibonacci number, do you have to work out the previous 9? And it's just kind of no, but also there's kind of a subtle distinction there. Right, okay. That was a really long answer. Is Fibonacci an iterative definition? So you probably get some initial information there as well. We'll see an example of that later on in one of these map questions that we're going to look at, where we're told the first term of a sequence, and we're also told how later terms depend on previous terms. The example at the top there, f of an, is a function of just the previous term. Fibonacci numbers is an example where it depends on the previous two. We're going to see an example where each term of the sequence depends, in some straightforward way, on all of the previous terms, which sounds complicated, but it's not that bad. Okay. I've got a bullet point underneath that third bullet point to show you this big sigma notation, which I'm afraid we're just going to recognise the way you read it when it says, let's split screen quickly so I can write something. The way you read that big sigma notation there is kind of, in my head, I read it in this order. Oops. So this says the sum from k equals 0 to n minus 1 of ak, which means a0 plus a1 plus a2 from 0 to, that was lightning again there, to a n minus 1. So if you like k as a kind of dummy variable, where you add up I really hope that came through the live stream, otherwise I just look like I'm staring out of the window at nothing. A0 plus A1 plus A2 plus A3 plus all the way up to n minus 1. So kind of the answer on the right hand side for what does this actually mean doesn't involve k. In some sense, you look at the right hand side and the question is like, who's k? What's this k? There's nothing, no k on the right hand side. A bit like when you've seen integration has a sort of dummy variable x, where your answer, if you do in the integral from 0 to n minus 1, with respect to x, your answer won't depend on x anymore, it'll just be a number. Good, right, now people did get the thunder through, and it was loud. Sorry about that. Oh, I realised somebody in chat has the username K. I want to be clear that you are involved in the live stream as well, just not on the right hand side. Good. Somebody's posted something from the Pearson VUE website, which says that their booking system is running more slowly than expected. So that's a thing. I am trying to stream right now. I'm trying to do the streaming. It's quite a lot of. Anyway, never mind. Right. I have an argument with the sky. It's not going well for me. Yeah, so sometimes, and somebody in chat has noticed that this sequence starts from A0, which is something that some people like, especially if you think the natural numbers should start from 0. Computer scientists love 0, in my experience. The disadvantage of starting from 0 is that you say the third term of your sequence, and you have to remember that that's A2, which feels like quite a psychic load to take on, but maybe they just say the nth term of the sequence to mean an. Makes me feel funny. How would you know? It would have to be given to you. You can't go around guessing these things. If it's your choice, then make sure you're consistent with yourself. If it says sum the first 3 terms and you decide to call them A0, A1 and A2, then remember that you did that. Okay. Time for a formula, I think. We've got this idea of adding. Well, no, sorry. Time for a definition of arithmetic sequence. you've definitely met these. If anybody's ever told you about triangle numbers, then as a warm-up for this sort of thing, we'll get there in a second. Here's an arithmetic sequence. So let's do an example. You've definitely met these. So I'm trying to write odd numbers on the board. The idea being that I have a first term, in this case a equals 1, and I have a common difference for the gap in between. You definitely met these with common difference. So you can predict what the next term is because you know a rule. If you like, this is an iterative thing where an is defined as a function of the previous one with that function. That function, let's give it f of x, is x plus d. But each time you add a constant amount, which is quite a boring function. I have all of these things that it could be involving like this Fibonacci jazz and all of this stuff or you could do anything, but arithmetic sequence, sometimes called an arithmetic progression, just adds. I guess the even more boring one would be the case where d is 0 and it's just the same. Let's try and talk about those. Good, okay. In chat, if you want to talk about a sequence, how are we going to do that? I don't know, sometimes people, just for chat today, if you want to do underscore, the way that I get the subscripts down here in the software that I'm using is that I type underscore, which is above the minus sign on my keyboard. If you are on a phone keyboard, I don't know where underscore is, but this a underscore n, if you like. And to be honest, if you type an, I'll probably know what you mean. That is advice for chat today. Okay, there's a formula for adding up these. We've met two things. We've met the idea of adding and we've met an arithmetic sequence. There is a formula for adding these up. It is on the screen right now if you've never seen it before. If you've never seen it before, we're going to just learn it, I think, for now. We could ask questions like, where does this come from? But let's say that you needed to add together these odd numbers. Well, a slow way to add them together would be to just do it. 1 plus 3 is 4, plus 5 is 9, plus 7 is 16, plus 9 is 25, wait a minute, plus 11 is 36. A fast way would be to spot a pattern or something. The formula here is that it's the number of terms, in this case 6. So I've got 6 terms, importantly, if I've numbered them A0, A1, A2, A3, A4, A5, because I'm a cool computer scientist, and I've got to remember that there are 6 of them, even though the last one is A5, because the first one was A0. 6 of them. The first one is 1, the common difference here is 2. The formula tells me that the sum is this, 2 times 1 plus 5 times the common difference. Or if you prefer, a nice way to think of this is that it's the first term plus the last term times the number of terms divided by 2. Which sometimes people phrase as the average term multiplied by the number of terms. The fact that it's a common difference means that average is quite nice. There's these pairs you can join up. So 1 and 11 have the same average as 3 and 9, have the same average as 5 and 7. That these things sort of balance on scales nicely as they come in. That's not going to be true of the next type of sequence that we're going to see. So think carefully about what's going on here if you want to use this. What's going on here, I suppose, is some idea of an average of the terms multiplied by how many there are. Some people really like this formula up there, n over 2 brackets 2a plus n minus 1d, but there's quite a lot in that formula to remember. So up to you. You can try and memorize that formula up there, or you can memorize this, or you can draw this kind of picture for yourself. To remind yourself that the terms are paired together. In this case, you'll have noticed that these all sum to 12, and there are 3 pairs. Although the argument is slightly more fiddly, of course, if there are an odd number of terms. The formula kind of claims that that's not a problem. I suppose the average term will be the middle term, so not a problem. Okay. What do I want? If common difference is 0, does it still count as an arithmetic sequence? Yes. I said we shouldn't talk about them, but it would technically be an arithmetic sequence if it had common difference 0. So Neat in chat is proposing the arithmetic sequence 1, 1, 1, 1, 1, 1, or choose your favourite constant. The constant sequence is arithmetic. You can even use this formula to add all those ones together, but I don't recommend that. Now really sunny, fun. Ooh, rainbows somewhere. We can look for rainbows. That is British summertime if I've ever seen it. Right. It's a +0. Good. What was I doing? I was in the middle of doing some sort of joke where I suggested that you could add these together by using the formula at the top of the screen to get n/2 times 2a plus 0. So n times a. Good. Right. Yes, and then in chat, brilliantly, Anonymous is 1 bullet point ahead of me because Anonymous says that's also a geometric sequence, which is true. Let's learn about geometric series. So this was an arithmetic progression, or arithmetic sequence. I'm going to flip between the two, sorry. We've got this idea that it's arithmetic. Let's write out the word arithmetic. It's on the screen, isn't it? But never mind. Okay. Another sort of sequence that I want you to know about is called a geometric sequence progression. I've got to pick geometric progression or geometric sequence. And you've met these as well because here's an example. Oh, I'm trying to multiply by 2 each time. I would like you to notice that these terms are quite a bit larger than the other ones that we looked at. Oh, times 2, not times 32. If there's 6 terms of a geometric progression, the idea is that you have a first term and you have a common ratio, which in this case is 2, but you should think for yourself about other examples. Where am I going? I'm going down here. There is a proof on screen. How do we feel about this? Let's try and get the definition first, and then I'll scroll down a little bit and we'll look at this proof. So there's the first term and there's common terms. So 1, 1, 1, 1, 1 is also a geometric sequence because first term 1, common ratio 1, common the constant sequences are, I think, the only ones that are geometric and arithmetic. Otherwise, these really are 2 different sorts of sequence that I'm telling you about. Good. The series refer explicitly to a sequence of partial sums, or does it refer to taking the sum overall? Good question. I need a dictionary for that, I think. My usage is a little bit more blurry than you would like, I think. Technical question about language in chat. Good. Okay. Yeah. So these are powers of 2. If I start with 3 here instead of 1, then it's 3 times the powers of 2. If you like, then I've defined each of these in terms of a kind of recursion thing where before we saw n plus 1 here, right? Before we saw x plus a constant thing, and in this one it's going to be x times r. Is that clear that I'm multiplying? Whatever, I'm multiplying by r, in this case 2. Maybe I should do r dot x. Something that people happy with. Something looked weird there. R times x. I don't want to do times symbol because it will look too much like me. Yeah, whatever. There we go. Good. Right. Okay. So we've got a first term, we've got a common ratio. You should also be aware of ones where it looks like division. You've probably met this sequence before as well, the halving sequence, which I'm going to write as multiplied by a half each time. I'm going to label that one twice for some reason, sorry. Times 1/2 times 1/2. You're welcome to think about this as divide by 2 each time, but I'm going to think about it as multiplication. Okay, so geometric progression here. Oh, and those are all off the screen. Fun. Okay. This one is more interesting to me because it makes sense to sum all of the terms. So there's maybe a thing you've seen before, that 1 plus a half plus a quarter plus an eighth is when it's a bit like you were sharing something and you were taking half of what's there lots of times, half of what's left. I think there were two somethings actually, because maybe someone took one of the two things, looking like they wanted to share. Don't want to be greedy and take both of them. And then there's one left. So being polite, you take half of what's left, and now there's half of a thing left. So they take half of that, and then half again, and half again, and half again. And eventually, you'll have got really close to between you having taken two things. Overall, won't be much left. We can do some maths for that. That's what I'd like to talk about. So if you sum these things, so if you want to do, let's do the first case just to demonstrate that you can do sums like this. It always makes sense to ask what the sum of a finite number of terms of a sequence like this is. The idea, if you like, is that you consider what would happen if you multiply this sum by 2. So if you multiply by 2, then you get 2, 4, 8, 16, 32, 64, which is almost the same thing. So if you multiply by 2, you get a 64, you lose the 1, and that was 2 copies of this. That's kind of where the formula comes from. I'd said that way too fast. I'm just going to quickly write down this, although I realised that this is not an incredible example. So the formula I've given you there is a times 1 minus r to the n, where n is the number of terms. 1, 2, 3, 4, 5, 6 terms again. 2, 4, 8, 64. There's my 64. I kind of regret giving you the formula like this. Obviously, we could put a minus sign on the top and the bottom to make it 1 times 2 to the 6 minus 1 divided by 2 minus 1. And sometimes it's good to write that down so that you don't confuse yourself with minus signs. I've got these slightly awkwardly, I've got negative numerator and denominator, which you can deal with. What does this make? This makes 63, I think. And having a formula for that is quite good. Let's look at the other one as well. So adding up the other one, 1 plus a half plus a quarter plus an eighth plus a 16th plus 1 over 32 is 1 first term times 1 minus 1 over 2 to the 6 over down here. I've got to remember how much space I've got. 1 minus a half. Which is, what is this? 1 over 64 here. So this is 63 over 64, very nearly 1, divided by 1/2, which is 63 over 32, which is very close to 2. You know, I said that we're getting close to sharing out 2 somethings. It's exactly 2 minus 1 over 32, right? And that kind of makes sense that if you added 1 over 32, then these would add up to a 16th, and then you'd have a 16th, so it would add up to 1 over 8, they would join together and give you an eighth, and they would add together and give you a quarter. If you've ever played the game 2048, where you make powers of 2, you have these like powers of 2 sliding blocks moving around, and you know, if you have blocks like this, and then suddenly you get another 1 block, and then it's great because you have an extra 1 block. You can join those to make a 2, you can join those 2's together to make 4, and then the 4's collide to make 8, and the 8's collide to make 16. You chain reaction your way up to eventually join together 2 32's to make 64. Another way of saying it is this sum, if you add 1 to it, you get 64 after some sort of chain reaction of adding together powers of 2. So you get 63. If you know about binary, that's the carry in binary. Sort of you hit the binary number 1111111, and then you hit another 1, and everything rolls over to 0, and you get the next power of 2. So like it's 1 less than a big power of 2. If you're adding up not powers of 2, then you may need to switch from binary. I mean, you don't need to switch to binary, but if you like thinking about binary and you want to do other powers, you might think about other things. Yeah. So for powers of 2, it's always next term minus 1. Let's look at powers of 3 just to check what's happening. I'm going to chase the first number as well. I'll be brave. So we're going to have first term 4, common ratio 3, and I'm going to write out several terms of this until it's kind of clear that I probably couldn't do this sum in my head. that's enough. That's 5 terms this time before I got bored. The formula says that I should write down 1 minus the common ratio to the power of 5, 1 minus 3. And again, I slightly regret the minus signs for this example. This is 4 times, so 3 to the 5 minus 1 is 242, and we're supposed to divide by 2. So I get 484, does that seem plausible? 420, oh, I said I couldn't do it. 432, 460, yeah, 468 plus number 16 or something. Yeah, seems about plausible. It could be 484. It's good having a formula. And the rule here at 484 is obviously not just 1 less than the next term. The next term would have been about 900 and something. So there's something else going on. Right. Yes, where do these formulas come from is a very good question. I think I used to have a revision thing about this, but we can talk about that in a second, I think. Yeah, it's not quite relevant for the MAT that you know exactly where these formulas come from, but we will get there, I think. Let's look at one more example. A is 4, R is 1/3. In this case, we have 4 plus 4/3 plus 4/9 plus 4 over 27 plus 4 over 81. And the formula says that this is 1 minus 1 over third. Oh, fraction down there. And this is, oh gosh, what's that then? 4 times 242 over 243 divided by 2/3. Yikes, that's a bit harder to work out than I thought it was going to be. Oh no, this is right. This is 484 divided by 81 or something. That looks roughly plausible. Oh, I don't know. Isn't that about 5? Oh yeah, it does start 4 plus, so it should be at least 5 1/3, shouldn't it? About 5. Yeah, 5 and a bit. Looks plausible. This one's fun because we can keep going. These terms are really small, and they're getting small. They're really small, really fast. The more of them I have, the smaller this term will get. Everything else is fixed. This is A. This is 1 minus R. This is 1. The more terms I've got, the smaller this thing gets. 1 over 3 to the 10, 1 over 3 to the 100. It becomes tiny. So the last thing I need you to know is that in some cases, there we go, that bullet point there. In some cases, you can sum to infinity, which means, if you like, what would happen if you had infinitely many terms? And the idea for this is that in our formula that we already had, this term gets really small, and we're just left with A over 1 minus R. So add them all, and you get 4 over 1 minus 1/3. This is a cool behaviour, I think, that, can I divide that in my head? So this is exactly, so 2/3, so I think this is exactly 6, which is kind of cool. Yeah, exactly 6 for the, what would happen if you added up all of the terms, or infinitely many of them. Good. So you're not expected to know where these come from, or really you're not expected to know what convergence means, which is a bit weird. In A level you learn the condition is that if the common ratio is between -1 and 1, then the sum to infinity converges. And you're not even really supposed to know what this means. In your head, it's okay to think about it as saying that the sum, the more terms you have, the closer it gets to a particular number, which depends on when you started and what your ratio is. You don't need to know a kind of mathematical definition of what getting closer means. So fair enough. Yeah, if you keep adding to infinity, how come the sum to infinity is not infinite itself? Because it will get big. The answer is that these terms are getting really small really fast. That there might be lots of them, but they're all tiny, so who cares? The picture that people sometimes draw looks like this. I will try and draw a kind of fractally picture for you. I want to draw it this size, I think. Can I get 4 squares on the screen? No, we'll just go for it like this. Okay, so let's imagine you've got a square. I'm going to try and show you a sequence which looks like infinitely many things, but not getting infinitely large the more of them that you've got. So here's a square where I've marked out 3/4 of that square, and then in here there's 1/4 of the square, and I'm going to do the same thing. I'm going to mark out 3/4 of the square. So I've now got 3/4 plus 3/4 of 1/4. I'm going to do it again. So if I zoom in here, I'm going to highlight 3/4 of this square, which is, oh gosh, it's tiny, isn't it? It's 3/4 of 1/4 of 1/4. If I keep going, then I hope you agree that this sequence of areas added together is not going to get infinitely large. It's going to get pretty close to the area of the square. The leftover corner is getting really tiny. And this is the sum of a geometric progression, because it's the sum of these terms where the first one is 3/4 and each one is getting multiplied by 1/4 each time. I'm scaling down my picture by 1/2 in each direction. Yeah, good. Okay, I like it with L's because it's clearly going into the corner. People sometimes chop in half and sort of chop and keep chopping, which we tried to do, sharing some objects earlier. Good. You're not really expected to know about divergent sequences. I suppose if the ratio is greater than 1, then you're in a case like this, where it clearly doesn't make sense to add together all of these terms to infinity, because, well, they're getting larger and larger. So your sum can't get close to a number, because adding this new large term would definitely make the sum much larger. With the formula for sum to infinity of the L's give 3, I think it's going to give exactly 1. I'm imagining that my square started with side length 1, so I'm sort of hoping that this geometric sum gives 1 as well. Let's try the formula. So the formula says 3/4 divided by 1 minus r. Good, that really is 1. Okay, good. So the dot dot dot's doing a lot of work there to explain that this is supposed to keep going forever. Sum to infinity is a kind of slightly different concept from just your regular adding together terms, and it only turns up, for the MAT syllabus, it only turns up here for geometric sequences. You're not expected to have any other understanding of what it means to add together infinitely many things, I think. Good. If we add up infinity, we should get infinity. Right, if you prefer, we are adding up finitely many things and seeing what happens when it's a very large number of things. Surely there's nothing wrong with that, right? If I have finitely many things, like I have over here, I'm allowed to use my formula, and the formula says it's 4 times 1 minus, do you really care? There's a tiny bit here. Do between friends, a tiny bit, not quite 1. Fine, not quite 1, but then divide by 2/3. And if you do that for a large number of items, not infinitely many, but a large number of items, then you'll get 4 times, really pushing it now really close to 1, divided by 2/3, which the only step I would like you to make is to say sum to infinity, whatever that means. Maybe it means nothing. Sum to infinity is this thing that you're getting close to, which in this case is 4 times 1 divided by 2/3, which is why I've written it down over here. Sum to infinity. If you like, in practice, in a finite world, we are adding finitely many things and we are getting very close to that number, as close as you like. That is actually pretty close. It doesn't sound rigorous, but it is pretty close to the definition of convergence that people learn at university, which you don't need to know. Hello chat, I've put you back on screen because you're asking good questions. Yes. Okay. Right, those are all the formulas that I need you to know, all of the things. We're going to have a quick moment here to think about why those are true. Not necessarily examinable, but somebody asked, so I'm going to do this, I think. For the arithmetic progression, I want to show you this picture, which I found out is due to Althusser, which is a mathematician from, I believe, the 11th century, Persian polymath. whose name is Latinized to Alhusen, but it might be more like Alhaitham. Right, okay, here's a picture. I need to colour it in though. Is there a colouring in tool? Not sure there is. Let's just go for massive. Can I turn the pen up? That's good. Okay. Here's a picture. In pink dots, I have 4 plus 3 plus 2 plus 1. And in green dots, I have 1 plus 2 plus 3 plus 4, which is definitely the same thing. So the argument here is that the number of pink dots is it's 1 plus 2 plus 3 plus 4. Also, it's, and then to find the number of pink dots, I can do this. This is a rectangle. 4 times 5 divided by 2, because there are 4 times 5 dots in the picture and half of them are pink. 4 times 5 divided by 2. And that multiplication is much easier than the adding. So you can do that in general, in some sense. If you have a sequence that's not 1 plus 2 plus 3 plus 4, but is maybe a scaling of that sequence. So to do the sum 3 plus 6 plus 9 plus 12, I would notice first that this is sneakily just a triple of the sum that I just showed you. And to do a sum like 4 plus 7 plus 10 plus 13, I would notice that this is 4 lots of 1 plus the sum that I just showed you. Those are enough ideas. Those are enough ideas that you can now go and work out the arithmetic progression formula from scratch if you want to. So if you struggle to remember it, if you can remember this picture, gives this answer, and you can remember these 2 tricks: a scaling trick to bring out a factor, and an addition trick where I've added 1 to each number. But that's predictable change in the sum, isn't it? There are n terms and I've added 1 or 2 or whatever to each of them. If you know those 3 things, then you can combine that knowledge together to get the formula. All it's telling you really is that to get an arithmetic progression, all you do is scale the terms and add a constant to the terms. You can allow for both of those things. You'll start with this basic fact from the 11th century and scale it appropriately with a nice picture. Do limits lead to Zeno's paradox is a great question. Does Zeno's paradox apply to the real world? It's the maths and philosophy response. You've asked that as if it's a real life problem to have Zeno's paradox. But isn't Zeno's paradox about the theoretical world and the geometric progression is about the real world, where things actually add up? You don't want to be on Zeno's side, right? Do you? Or maybe reality is like that. If you haven't seen Zeno's paradox, please Google Zeno's paradox. Well, don't. I mean, I'm just saying that because it's fun, not because you need to know it. I should stick to things you need to know. He says, doing a proof of a formula. Let's do the geometric one. So the geometric one. So there's a line on screen. Let's have a look at it. It was just up here. This kind of line of this line of arithmetic on the screen is to say, see what happens if you multiply the sum by 1 minus r. Everything collapses down. That's called a telescoping sum sometimes. You're supposed to imagine one of those telescopes like a pirate would have, where it's lots of sections. Fans of the art stream, here we go. Lots of sections of telescope like this. I've never been able to find a good Google image result of a telescope that looks like this. Okay, telescope. You look in this end. No, wait, you look in the small end. Piracy 101, you look in this end. And you see someone who's miles over here, but you see them large because you're looking through your telescope. They collapse down for easy storage aboard your pirate ship. This bit fits into this one, fits into that one, fits into that one, and it kind of collapses down. That is what's going on in that sum up there. It's called a telescoping sum if you want to look up more, because if you find that interesting, then there is a way to find out more. And that gives you a nice tidy formula instead of having n terms to have just 2 terms with some division, but just 2. Right. Any tips for sequences where you have to rearrange it to get it inside itself and then cancel out, like the Fibonacci sequence divided by 2, then 4, then 8, then 16? That sounds a bit like one of the long questions that we're going to see. In the question sheet, there's some messing around with Sn. It's really hard. It's a S subscript n. It's this sequence where we're adding some stuff and it's all divided by powers, and we're going to add those instead. It's good fun, but it's quite tough. We will get there. Let's save it for that one. Oh, right, phew, goodness, one person couldn't hear me. I was actually trying, so pretty good. We've got some revision questions. Some of them this time are a little bit more straightforward than some of the other ones. Somebody asked in chat, are you supposed to be able to do these without hints? And for some of them, the answer is yes, you're supposed to be able to do this, just looking at the revision notes. For some of them, you might need hints, because some of them are supposed to be a bit harder, or if you like, some of them involve a bit more of a problem-solving thing. We're going to do a vote in chat to say which questions we should focus on. And just to be clear to that one person who's just asked, proofs of formulas will not be required. They're not on syllabus. But it doesn't hurt to know it, does it? I always like to say, if you can remember the reason why something's true, then you can play with it, you can remix it, but you can also remember it. That's how it works for me in a lot of formulas anyway. It's a mix, isn't it? Some of them you want to just know, like the quadratic formula. You probably don't want to spend too much time reinventing the quadratic formula every time you need it. But then some of them, it's good to know them. You might as well. You can get a flashcard or something. We have MAT flashcards if you want them. But yeah. Right. Okay. Would you ever have to rearrange an iterative sequence into one in terms of n? And then the example they've given in chat is a very A-level kind of thing, where what sort of thing? I think we're going to solve something later on. Yeah. Same question, maybe? Yeah, same question. We're going to solve something. You're not expected to know any of the theory around. In chat, somebody's asked me about a recurrence relation, so something defined by iteration involving constants. Let's see the vote. The vote is a bit wow. I want to talk about the Catalan numbers because they're hard. I like the Catalan numbers. Last questions. Are the last questions more likely to be logic-based as the maths for computer science students too, especially since there isn't a choice anymore? Obviously, we can't tell you what the questions are. Sorry. I wonder if it's the same person who asked about logic questions before. They've decided that there's logic questions. Oh, fine, okay. Would you mind recapping the part with capital L? Emma, I don't mind. Which one's that? Part with capital L. I don't know which one that was. Oh, it's the periodic. It's the last bullet point. I didn't read it out. Thank you. You asked politely, and I had skipped a bullet point at the end. Hide the thing quickly. There's a bullet point right at the end there, which talks about a periodic sequence, and then I've tried to define a periodic sequence, which was harder than I thought it would be. You sort of know what it is, right? I think. It's a sequence that repeats. So if your sequence was like this, so not arithmetic or geometric in this case, then I would say that's periodic with period 3, because you have to go ahead 3 terms to get to something that's the same. And wherever you start, if you go along 3 terms, you see the same thing again. The definition is a little bit wonky. It looks a bit weird. The minimum such L, right? Because it's also true, looking at that one, that if you jump 6 squares along, and this is a bit awkward, but if you jump 6 spaces, so from here 1, 2, 3, 4, 5, 6, then, well, it's periodic, I suppose, where every 6 it repeats. But that's not really the period of the sequence. That's not really what people mean by the period of the sequence. When you saw me writing it out, you didn't think, yes, it repeats every 6. That's a true fact. It repeats every 6, but the thing I should define, I think, is the minimum such number that you can always jump along and it repeats. Such a mouthful to do it in words, look. The least such number that it No, because it's got to be for all. There's got to be a for all in there, for all n. So it's not just a coincidence. It's not just 1, 2, 1, 3, 1, 2, 1, 3. You've got to be careful because this one, there exists. So this one down here, 1, 2, 1, 3, 1, 2, 1, 3, is an example where it's periodic, and the period really is 4, even though you can jump 2 squares and always see the same thing, but the period is 4 because it has to be the case for all starting points, not just your favourite starting point, that jump is enough. So the definition is super wonky, but it's like that for a reason, that sometimes trying to define these things really precisely looks a little bit messy because you end up ruling out all the special cases that people might be worried about. Definitions are so important in maths. Right. Good. Right, what's this? People are asking about this. If we know extra formulas, can we use them? And this person knows an extra formula about the CN numbers. You would probably want to prove that, I think. Unless, well, if the question genuinely just says find these numbers. Mr. Morale, you'll like this. Right, let's stop this voting. So 14 is definitely first by a mile. And then some it's 4 and 7, which is interesting to me, and 5. I'm not saying the questions are in any particular order, but there we are. Mr. Morale says, can the STEP Foundation course be good preparation for the MAT? You'll love this. On the official Oxford MAT page, I'll just show you what I've done. On the official Oxford MAT page, so information about MAT, we've literally linked to the Cambridge STEP Support Programme. I mean, also this one, running with Oxford, welcome to the show, but also we've linked to the STEP Support Programme because we think it's good. So to answer your question, yes, we've even put it on the official Oxford website. We think it's good. Imagine that. Right, okay. I don't want to have to hand in my whiteboard stuff with my previous working out in case I want to check later. Yeah, okay. Yeah, noted. Okay. What if a term so if a term reappears in cycles and the filler items are random, I would say that's not periodic. I'd say it has to be periodic for any starting point. Your worst enemy chooses a starting point and inspects and says, oh, is this a periodic sequence? Is it repeating? It's a definition, right? Okay. Right, we're going to have a look at 14 and 13. These are ones that people are asking about in chat. Here's 14. Oh, I can get both of them on screen. There we go. Lovely. Because we've learnt some maths a little bit behind, but that's all right. So this sum is quite strange, isn't it? This is testing, I suppose, whether you can expand out this sum to work out what it means. Let's do an example of what this means. So example, it's the first ones that are tricky. So I'm going to slightly cheekily do an example with n equals 3, where this is C4. This means the sum from I is 1 to 3. I'm plugging in n equals 3 everywhere. Ci, C3 minus I. Okay, so I've chosen my value as 3, just to give you an example. It says C4. Oh, brilliant, that's one of the things I care about. C4 is the sum from I is 0 to 3 of these things, which means that I'm supposed to do a kind of for loop, if you like, computer scientists in chat. A sort of for loop where I am also summing as I go along. So first I put in I equals 0, and that gives me C0, C3 minus 0. And then I put in I equals 1, which gives me C1, C2. And then I put in I equals 2. And I keep going like a computer with a for loop until I get to the stop condition, which is I equals 3. So something like this. Which is pretty, but I only know C0 at the moment. I don't know C3, 2, and 1. Let's do another example. That's 2. So I'm going to try and write this one out just using this pattern that it's. Oh, that was fun. So as I write out these CI terms, the first thing here, C0, C1, C2 is going up because I'm going from I equals 0, and I stop when I get to the number n. And at the same time, n minus I, where is it? N minus I over here is going down. The first thing I write down is Cn, and then I write Cn minus 1, C0. And of course, I don't know what the values of these things are either, but we're getting somewhere. N equals 1 says that C2 is C0, C1 plus C1, C0, which is kind of nice. And then the only case left is N equals 0 to think about. which tells me that C1 is, and now this is a little bit controversial, isn't it? Because the stop condition is hit straight away. So I think this is a sum where you put in I equals 0 first, and you stop once you've done I equals 0. It kind of includes the stop case. Fans of Python will be disappointed there. Sorry, I'm talking about computer science. So I think this is C0, because I'm putting in I equals 0, C0 minus 0, which is also 0, and then stop. So I think it's just C0 times C0. Ah, brilliant. Okay, so I know that this is 1, and then this is 1 plus 1. 1 plus 1 is 2. Welcome to the Oxford MAT Livestream. And then this is something like, gosh, 2 plus 1 plus 2 is 5. And then this is, after a lot of work, 14, I think. But expanding them out like this, the idea of this was not really that you would work these out. What I wanted you to think about was this. What does this sum actually mean? And if this is weird to you, then I would practice this. So getting from here to here, I'd like you to check that you can do that. I think I mean write it out and check that you know when to stop and why you're stopping, and you know which subscripts you're writing down at each point and why. That I think is the important thing. Right. Okay. Somebody has just joined, so they're going to rewind and watch the stream at double speed. So I've got to talk even faster. Okay. Good. Right. Okay. Catching the chat. Are they happy? They're happy enough. These are called the Catalan numbers. If you want to ever see them again, this property is surprisingly common. This idea that you add together previous terms, multiply together, but forwards and backwards at the same time. It's weird to me that that comes up ever. But all of the ones where the subscripts add up to n. So you can do all this like partition stuff where you want the subscripts, you have to do some chunk of it and some other chunk, and the chunks are in some sense adding up to all the different ways to split it. There's a lot of counting problems that are a bit like this. Don't worry about it. Okay. Just to tell Georgina, they do take whiteboards off you during the exam. I'm also going to type this. Because it's important. The system is that you can replace them. So you can ask, we're going to put this on the screen as well, just to do it. The system is that you have to hand in your whiteboards to get more whiteboards. There is not an unlimited number of whiteboards in the world. That's the system. Okay, that's 14 Catalan numbers. Let's look at 13 as well while we're doing this. I can see in chat, Jacob's going to ask, should I prioritise thinking about MAT revision or thinking about personal statements? Obviously, I think you should think about MAT questions. So sequence is defined by A0 is 3, and then for A, and then afterwards, you add together all the previous terms. This one's related to a MAT question that we're about to do, so let's have a look. So A1, you add together all previous terms, okay, which is just 3. So I guess this is sort of quite a trivial sum again. All previous terms just means that 3, so off we go. And then A2 is add together all of these, which gives 6. And then A3, you add together all of these, which gives 12. And then A4 is you add together all of these, which gives 24. And at that point you think, hang on a minute, these things are doubling. Not the first time, but these are doubling. So I would say this is 2 times, this is 3 times 2 cubed. So my guess is that it's 2 to the n minus 1, 1 fewer. How many doubling? How many 2s have you got? 1 less than the number down here. There's a bit of a delay at the start before it starts doubling, and then it starts doubling. Check that for 1, check that for 2, check that for 3, check that for 4, and then think, right, why does that work? So I suppose the reason that works is that this sum is a geometric sum. If it really is true that they're like this is a geometric sum, and then we're adding 3, and it just sort of checks out. So I can sort of do a check over here if you like. That's the answer that I was hoping you would get. But check that 3 plus, and then what do I want to do? 3 times 2 to the n minus 1. I want to check that this really is 3 times 2 to the n, the kind of next term in this sequence that I'm claiming. And this bit's geometric, so this is a good chance for us to practice our formulas. The first term's 3. 1 minus 2, there are n terms in here, including the kind of 2 to the 0 term at the front. And there's a plus 3 on the front. I think I'm going to be out. No, I'm not. This is all good because this is 2 to the n minus 1, and then I'm adding on 3 again. I got worried about this minus sign, but there's also one up there again. Good. Okay, so this really is 3 times 2 to the n. Smiley face. Proof. Good. Okay, I wasn't sure. I'm not sure I was expecting you to do this kind of check to check it adds up, but geometric sequence formula is all good. Oh, right. Yeah. Find a. The question says find an in terms of n for n greater than or equal to 1 at the end of the question there, which is important. Someone in chat says that your formula doesn't work for a0, and I'm not claiming the formula works for a0. Let's be more explicit on the screen. There we go. I'm not claiming that holds for a0. I'm not being nasty. Yes, but good spot. That formula does not hold for a0. Are questions 6 and 7 of previous math papers worth doing for practice if you're a math student? My hot take is that yes. Questions 6 and 7 of previous math papers are interesting, and I sort of think math students should be able to do them. Or be able to try them just like you try questions 4 and 5 on old math papers. The syllabus is the same. It's been the same. So you're expected to know the same maths as the computer scientists. Nothing's changed there. If you are a computer scientist, you are expected to know the same maths as yourself. Oh, I should flip the statement, shouldn't I? Never mind. Okay, good. Would C1 not be C0 squared equals 1? Yes, I thought I did do that, didn't I? Yeah, C1 is C0 squared. What does it say in chat? I agree, C0 squared, which is 1. Okay, I always find these questions in chat sometimes, the question is in the negative, right? So it says, for the Catalan numbers, would C1 not be C0 squared equals 1? But it is. So I think the answer is no. Okay, right, okay. Emma asks, are you expected to know series? And you're only expected to know geometric series and arithmetic series, the two that we've looked at in the revision notes. There's probably other things that people can sum out there, but for the math syllabus, you're only expected to know series. Somebody would like a formula that also holds for n equals 0, and so they are not going to like it, but here's my cases. You don't like it, do you? This is not what you meant. So case 3 if n equals 0, or 3 times 2 to the n minus 1. This is supposed to be a curly brace. This is what people do sometimes if there's different cases. Do this if it's 0, do this in the other case. That's probably not what you wanted, is it? You probably wanted something fun involving a function that's 1, 0, and 0 everywhere else, or something like that, which you're welcome to build. People have funny ideas about what functions are sometimes. I think that's a function. I think that's fine. Good. That you don't like that? Yes, okay. In chat saying they don't like it. Cool. Right, okay. Challenge for you in chat is something like, so use a function like this. So the thing is that if you put in n equals 0, you'll get 3 over 2. You need to add an extra 3 over 2 to this formula, but only if n equals 0. So the way you might do that, if you like floor functions, is that you might do something like this. So that this number gets rounded down to 0 almost always. Floor of 1 over 1 plus n squared almost always gets rounded down to 0, and this term's not here. This is all multiplied together. But in exactly the case 0 is 1 over 1. So you round that down, you get 1, and then you're adding your 3 over 2, just in that special case. So final answer, this. You see, I think that's nuts. I think that's really silly, because it's slightly case-based off this floor function anyway, which is why I'm deleting it. Cool. Matt, it's 2.5 hours and there are 25 marks worth of multiple choice, 250 marks. Is there an amount of time recommended to say for 2 long questions? I'm not going to go as far as recommended. I'm going to say what I would do, where the people in chat are different from me. I think I would do is I would leave about an hour for the 2 long questions. I think I would try and do multiple choice questions for about an hour and a half. I would leave about an hour for the long questions, and probably an hour is a bit long maybe, so I might come back to some multiple choice questions in the last 15-20 minutes maybe. And actually I find it quite hard to focus on tasks, so I'd probably jump around quite a lot. But I think personally I might even do them first. You can use this navigator thing to jump to the long questions. I think personally I would jump to the long questions and spend about an hour looking at them total, maybe not all in one go. What would I consider a good percentage? I always say that 70 or more is a good score, but I'm never guaranteeing anyone any particular outcome when I say that. There's no pass mark on the map, so yeah. Okay, I think I'm going to leave 4 and 7, the other ones we looked at. 7 really quickly, to check. For 7, the question is asking, oh, I've got lost 7. I know it's on screen, sorry. My eyesight is so bad, there we go. 7 at the top there. The question says, when does that converge? And the idea is supposed to be that, okay, there's a number x in there. I would like to know, is x larger in magnitude than 2 or not? The idea is that the terms are supposed to be getting smaller, or closer to 0, I think I should say. If they're getting further from 0, then your sum is just going, maybe you're adding a lot and then subtracting a lot and then adding a lot and subtracting a lot. What are you doing? For this to converge, you need the common ratio, which in this case is minus x over 2. You need that minus x over 2. We need to be between -1 and 1, which in this case is negative x divided by 2. I'm putting the negative in just to highlight that that really is a geometric series with common ratio minus x over 2. And this simplifies a lot. So this is true that if x is between -2 and 2. In that case, you can use your formula, and then it's all good. Right. Oh, my eyesight, I really had to zoom in there. Okay, right, there you go. So in chat, someone's put x less than 2, and let's be careful because we want it to be between -2 and 2, not too negative. If you make it too negative, then like if x is -4, for example, then oh my goodness, we're talking about the sum 2 plus 4 plus 8 plus 16. Don't want that. That's bad. Okay. What else is chat up to? Something involving square roots. So I'm going to think about that. No, square root of x squared, my least favourite thing. No, I like square root of x squared really, I suppose. To get to choose, booking opens on the 18th of August. This question about booking maybe depends on your test centre. Yes, when booking opens, you will see what is available. Is the maths score personal statement both looked at before interview offers? Yeah, so before we invite anyone to interview, we wait for everyone to have a go at the maths, and we also look at people's UCAS applications. We look at both. It's not just math based, we look at other information as well. Good. And question in chat about partial marking, which I'll just put on screen. I'm going to take a short break in a second. Can you be awarded a partial credit? Yes, you can. For those long questions, which have got multiple parts, each part is worth a certain number of marks, and you can get partial credit. We should really do some math questions, shouldn't we? Yeah. Important is math versus interview, is it 50-50? It's a decision made by humans, so it's kind of impossible to say. They're both pretty important. Obviously, at interview, we've now met people and done maths questions with them. Sometimes we've got them to do harder questions than math questions, and that's quite interesting. Sometimes we've met people and they're really good at other sorts of maths. Those are sort of interesting times. But we still look at the maths scores because maths that's 2.5 hours, which is much longer than an interview. So performance on 2.5 hours of maths is still going to be interesting. Right, so let's reset that down to something like that. That is good. Okay, if you've been looking at your screen for an hour, remember to look away and remember to not look at screens all day, every day, which is what I do. I've considered just switching to a sort of VR headset, which is just screen all the time, because I spend so much time looking at screens. Worth it though. Can you see the question on the screen? There's one up there. This is from 2016, and it was question 1A, which in 2016 was the first question that people saw when they opened the test paper to look at the questions in 2016. Surprise! It's a sequence. So even though for some of them this was material that they'd learned relatively recently, it turned up at the start of the test. The test is not, I suppose, what I'm saying is the test is not sorted by content in the order of the syllabus. Like we've been working through the syllabus in these MAT live streams, the test is not required to be sorted in the same way. Topics can get combined together, which we'll see when we look at more past questions. But also, your least favourite topic might be the first thing that comes up. I've mentioned interviews now, so people want to talk about interviews. Very quickly, Oxford interviews multiple times. For maths, it would be normal to have 2 or 3 interviews. Each might be about 25 minutes long. Each might involve 1 or 2 maths questions with multiple parts. The interviewers are there to help, and the interviewers are there to try and give you hints or change the question, either to make the question easier or to make the question harder. You are encouraged to listen to the interviewer and ask for help and to ask for clarifications if you need them, because they want to see you succeed. They want to see you do maths. That's maths interviews anyway. If you're applying for a different subject, like English language or something, then I think it's all different. But computer science as well is also going to, by and large, ask maths questions, in my experience. That's not a guarantee. That's my experience of what those interviews tend to be like. I don't think you'd go too far wrong by practicing some maths before a CS interview. How much do you care about AS results? Not a lot. We often don't have them. If you have them, then I hope they're good. If you don't have any AS results, then that's normal. Right, okay. Good. We're going to try this question. I think I'm going to do, unless anybody objects, I'm going to do short questions quite quickly, because I would like to talk about both long questions, if I can. Let's go. So, it's 2016, here's this question. I'm going to write a quick hack. This lowercase l, I know it's going to cause me problems. I'm going to write capital L instead. This is a sort of hack. You can do this in lots of different parts of life. If somebody's used some notation you don't like, if you explain calmly, you might get them to use different notation, or you might at least explain that you're going to use different notation. I just know all these L's are going to cause me problems. There's also numbers in there like 14. Okay, so the first one, A1 is 1. Yes, again, now I'm not panicked. A2 is, well, they're getting multiplied by L each time. So let's work out a few of these. I can see a pattern. I mean, it's a geometric sequence, isn't it? In particular, I care about the first 15 terms, and we started at 1, so I care about A15, which is L to the 14. Okay, well, I kind of see the pattern, right? There's a relationship between n and these. I suppose you could think about a geometric sequence being defined iteratively, or you could think about it being defined by a formula. A pretty predictable thing that's happened here. The first term has been multiplied by a ratio a predictable number of times, often a times r, often n minus 1 times, although do be careful with how the starting conditions worked. Whether you started at 0 or 1 might matter. Have to be careful. Okay, so we're asked for the product, which means multiply. So we want this times this times this times this times, oh my goodness, multiplied by L to the 14, which is a little bit of powers from the powers and logarithms section. the same thing as being asked what this is. And at this point, maybe you know about triangle numbers, or maybe you know about arithmetic progressions. So I suppose the joke of the question that it was a geometric sequence, but the thing we actually have to do when we calculate is an arithmetic series. Maybe that got you, I don't know. So in this case, I could use a formula here. I think I probably will, just to prove a point. I'm ignoring the 0. I just don't like it. I'm going to sum from 1 to 14. The formula for this says there are 14 terms, and the first one is 1, and then I put here 13 times the common difference, which is 1. Panic. There are 14 terms. What have I done wrong? I've done something wrong. n minus 1 times d. I've got the formula wrong. I'm supposed to put twice 2a in my formula over here. Whoops. 2a. 2a plus n minus 1d. There we go. Yeah, shouldn't have used a formula. Should have thought about what was going on. Which is, I think, 7 times 15, which is 105. Okay, so I get L to 105, which is d. And this is a good example of a question that kind of combines together the geometric progression fact, which you probably need to work out what's going on for this sequence, with then, when you do the calculation, an arithmetic fact. Good. Okay. Next one. Here's a new sequence. Oh, I do like this style of question where it looks absolutely impossible because, well, we've got this complicated property, right? We're told that each one is a ratio. Let's work out some examples for 4. It says 4n greater than or equal to 2. So obviously the thing I want to try is putting in n equals 2. What does that look like? You know, I could put large numbers in, but let's check 2 first. n plus 1, n minus 1. Okay, so a3 is a2 divided by a1, and that's going to sort of keep happening in some sense. That pattern is going to keep happening. Yes, chat was talking about something else. Chat's catching up. Yes, sum from 1 to 14. If you remember the triangle numbers gives you a faster way to write down that sum. I thought I would use the formula, and I regret it. But maybe that's just me. Oh, I've been given a1 and a2, so I should work this out, shouldn't I? It's 6 divided by 2. 6 divided by 2 is 3. Okay, well then, okay, that gave me a3, so maybe I should work out a4 next. Equals 3 will give me a4 is a3 divided by a2, which, oh, now I know a3 is 3. I'm going to keep going. a2 is 6, so this is 1/2. What have I got so far? A sequence that goes 2, 6, 3. Oh, I could just write them down over here. It's the ratio of the previous two. 6 divided by 2 is 3. 3 divided by 6 is 1/2. 1/2 divided by 3 is 1/6. 1/6 divided by 1/2 is 2/6, which is 1/3. 1/3 divided by 6 is 2. Right? 1 over 3, 1 over 6 times top and bottom by 6. 2 over 1. Good. 2. Brilliant. None of that happened. 2 divided by a third is 6. 6 divided by 2 is 3. 3 divided by 6 is 1/2. Yeah. Ooh. Yeah. Or you can substitute. Oh, I like that. That's a good chat message. I like that. Or you can substitute. Yeah. You can substitute to. Oh, it's gone. It was there. Oh, it's pending again. I liked it. I'm putting it back. There you go. We've restored it. You can sub, and it's the reciprocal of. So this one gets flipped over, which means that you have this predictable sequence where after not 3 but 6 you get back to where you started, which means that this is a periodic sequence. Every 6 times it repeats. Right, this was a1, this is a7, and long story short, I think 2017 is also in that pattern, being 1 more than a multiple of 6. So I think the answer is 2, which is D. Yeah, it's periodic. And that's an example of a question where if you don't work out the first 6 terms, then I really don't know how you're going to make progress. I guess the algebra thing is perhaps that you need to, if you do the algebra, then maybe you could notice after lots of work, relating terms backwards, that you could get back to an is equal to an minus 6. Oh, that sounds like work. Let's quickly simulate what that would be like. An minus 2, and then you would use that form again. So like if n is greater than or equal to 7, then that's a bit cheaty to write 7, but never mind. I've written 7 because I know where this is going. So an minus 2 divided by an minus 3 divided by an minus 2, which is 1 over an minus 3. That's quite nice. Okay, so then just sort of keep going. So then an minus 3 is an minus 4 divided by an minus 5, and then an minus 4 is an minus 5 divided by an minus 6, an minus 5. So then this flips over and you get an minus 6. That wasn't as bad as I thought it would be. Got to underneath chat a little bit. So an is equal to an minus 6. So sort of flip it backwards. I have to do 3 equalities because the cancellation gets me down a step. The cancellation made that much nicer than it could have been. In general, a fact like that feels like it should take about 6 bits of work. It only took 3. I've got 6 equal signs, I suppose, on the board, but 3 of them are kind of easy from doing cancellation. Interesting. Quite like that. Right, okay, so good news that the options are there. You can select a likely option if you like. I wonder how many people picked 3 over 2 for this question. So I think the sequence is never 3 over 2, so it's a weird pick for a 2017. I'm sure encouraging you along the way, I suppose, that as you're working out these terms, well, some of these look familiar. I'm surprised they're not all there. I suppose there's 6 things in the sequence, so too many for the options. Okay, good observation. Take logarithms and see what happens. Yeah, fair enough, I suppose. That sequence turns out to have complex roots, so you're using logarithms, knowledge about constant sequences with constant coefficients, a general formula, and then you're going to use de Moivre's theorem at the end to get back to this periodic sequence. There's probably a step question where you need to do all of those things, but not for math. Okay. Right, last one. This one's in the thumbnail, so we should probably think about it. It's another one where each term, in words, each term is the sum of all of the previous terms. That's what that xn formula says. It says, do some adding, add starting from k equals 0 to n minus 1, and that means add all of these previous terms xk. So like before we saw a sequence where 3, 3, 6, 12, and then doubling. This one does the same thing, except this one starts with 1, so it's actually xk is 1, 1. I suppose when k is, oh dear, when k is 0, it's 1, when k is 1, it's 1, when k is 2, it's 2, and then it gets into doubling. These sum to 8, and then 16, and 32, and so on. We're asked to take the reciprocals of these things, 1 over, and add them all up. And we're stuck, of course, because this is not a geometric sequence. It's not a geometric series that we're asked to find, because it's not true that there's a common ratio. It's almost true, though. It's almost true. Because if you put your thumb over this term at the front, then you get a geometric sequence. This bit in square brackets is 2. Either using the formula or just, I've seen this sum before a few times. 1 and a half and a quarter and 1/8 and 16th, halving, 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 halving. Going to get closer and closer to 2. 1 plus 2 is 3. Good. Yes. Just, in chat, Georgina in chat again. There was a question down there. What made you know maths was right for you? The chat. We can scroll up. I think I'm not going to answer this live. Maybe Georgina has an opinion. I know that we did a social media video recently about when did you know that you wanted to do maths, talking to people around the building. So if you're following Oxford Mathematics on the main social media account, this is our second channel. If you follow the main account, we've done when did you know it was maths as a series of videos that we've done. Good, okay. This is not too bad once you work out some terms. General advice for sequence questions, work out terms. This one is D as well. I haven't even shown you the options. This one is D, which we've done. Chat spotted they're all D. There you go, there's an arithmetic progression of terms. The answer is constantly D. Good. Okay, sort of rush through those. If you want slightly more detailed solutions on the Mat Live page, as well as getting the questions and the revision notes, there's also a solutions document. I'm aware that a couple of times in there I've used a formula like this, the fact that this is 2, or the fact that this is this. I got that one wrong, but only just. And if those formulas are new to you, then something you might practice is getting better at applying them, or something like that. Good. Credit to Anonymous in chat who spotted that we've picked questions where it's D as the answer. But it's time to look at some longer questions. Let's do that. I'm going to scroll down. Okay, down we go. We've got 2. I'll scroll past all these hints. If you look at the worksheet, you also get hints for the math questions. There you go. So we've got this one, which just about fits on the screen all at once, which is kind of exciting. This question is about sequences xn and yn. The sequences are not arithmetic progressions and they're not geometric progressions. They're just sequences. This question's here because it's one of my favourite questions of all time. It's just brilliant. We can talk about this question if you like, with all of its approximations for large values of xn over yn, this mysterious property that xn plus 1 squared minus twice yn plus 1 squared is the same thing as that with n instead of n plus 1. Large values of x and y such that x squared minus 2y squared is 1. We can talk about that question. We've got a question that is much harder, which is this question 5 from 2016. There's a sum at the top, which I suppose we can't do because it's not geometric and it's not arithmetic. But the question's got a lot of geometric inspired things going on. And at one point we literally have to do a geometric series. So that's going on there. It's this SN business. This is an example, by the way, where we've got this Fn, which is a formula. Suppose that Sn is equal to this formula with constants A, B, and C. Work out the constants. Somebody ages ago asked, are you expected to know this sort of maths? And you're expected to be able to join in with it if it's happening. Check this formula works for certain choices of the numbers. Go and find out what the numbers are. Occasionally maths works like that you have a lucky guess for what the formula is. You go and work out numbers to make the lucky guess work. Both questions have got a little bit of that going on. And okay, so second, and then later on the question gets a bit harder because we have these, we solve for A, B, and C, so we have a formula for Sn, hooray. But then later on we have these other sums, this Tn thing, which looks a bit like Sn maybe if you squint. It's got 2, 4, 8 in there. And Un, which doesn't look much like that. I guess it's got 2, 4, 8 is in the Tn and the Un, but not in the Sn because it was multiplied by 3 as well. So it's kind of got the n's backwards or something. So there's this kind of hard question of what's going on here. And then finally it asks you to add the s's, which is really tough. The s's are already sums. I guess we've got a formula for them by that point. Right, what do people want to do? What would you like? There's one vote in chat for continued fractions. And I can see one looking at the last 2 parts of this. The last question is, so voting for the last question, Rosie wants 2008. Or okay, let's let people vote a little bit. I haven't got a poll for it, but it seems a bit like it's maybe 1 vote for 2008. 2 votes for 2016 at the moment. I'll give people a moment to choose. The only way you can do this, I think, this last bit. So IV is a bit of, you have to spot what's going on, which is annoying because it can take an unpredictable amount of time to spot the relationship. I'm going to show you the relationship and I'm going to try and explain how I thought of it, although I've seen this question lots of times, so I might be remembering a memory. maybe you can tell me in chat how you thought of it, if you've managed to spot the link between TN, UN and the original definition of SN. I'd be interested to know how people thought of this. And then that's some of the problem. I think you can only do that if you really engage with the fact that you've got a formula for it by that point. And then it's one of these things that someone mentioned where you use the formula for it inside itself somehow. Harder question, second question, both questions, harder question. Right, okay. I'm going to look a bit about 2008, maybe only for 10 minutes, because I said it was my favourite. I know that's not quite how voting works, but let's talk about this really quickly. Okay, we'll do 10 minutes on this and then switch to 20 minutes on the other one. And we'll see if we overrun, we overrun. Okay, so first part, you've got to try some numbers, I think, until you spot that this works, or something like this. I think you're probably allowed 1 squared minus 2 times 0 squared, which feels a bit cheeky, but whatever. Is 0 a positive integer? Not sure. I think it's fine for that question. People marking it will have seen that happen and then thought we should have said what positive meant, I imagine. Part 2, I always go down the page, don't I? So part 2, we're asked to find values that, find positive values for A and B that this works. So this is kind of some magic guess such that, and there's weird expressions to say that 3xn plus 4yn, I'm already substituting. I'm that keen to substitute, minus twice, and I don't know what A or B is yet. But I do know that it's supposed to be, for some reason, x squared minus 2yn squared. So this is just sort of synthetic stuff for me at the moment, that I've got this kind of expression where I just need all this stuff to work out. And crucially, I can see on the right hand side there's no xn, yn. So what I really want is for this 24 xn, yn. There's some more xn's, some yns over here. Minus 4ab xn, yn. I really want that to be 0. So I really want ab to be 6. I suppose I should also work out the xn terms. I put ... I know I'm coming around to them. So there's like 9 xn squared and 16 yn squared. And I suppose I want these to match up as well. Minus 2a squared x squared. But I'm sort of thinking about coefficients. So I really want these to work out in kind of separate coefficients. Technically they don't have to, but it's the only way I can see to make this true for all n. And without working out all of the numbers, let's just make it true for all x and y. That seems, it's slightly overkill technically, but it turns out you can do that. So what have I got? I've got 9 minus 2a squared. So I want over here ab to be 6. I want 9 minus a squared to be 1. Do I? 9 minus twice a squared. I missed the 2. So I kind of, so maybe I'm told they're positive numbers. I'm told they're positive. I guess I want a to be 2 then. And I want, last thing that I want is for the yn squared stuff to work out. And that's 2b squared. I want to be minus 2. So I think I want b to be 3. And then I look back over here and I realise that, hooray, ab really was 6. And it's kind of amazing that you can do all 3 of these things. You can make all the coefficients check out. With a as 2 and b as 3. There's some sort of synthetic nonsense at the moment, I suppose, that you can choose numbers that make this true for all x and y. The reason I like this is that the question wants you to understand why you've done that. So important for anybody who's got to explain something later on. The question, look, it goes from that, which is just sort of some algebra bash, to like, oh, just choose values, choose numbers that work and make all these equations work out. Happy that we got them. What's next? Next thing is really to think about why you've done that, what that means in words. The only way you can do this kind of last part, I think, or this on the screen, maybe you could just guess large numbers. It says they have to be bigger than 50. That's not that big. You could maybe just guess numbers. The only way I can think of is to realise that that statement says, with the equal sign in the middle, that says on the left. x squared minus 2y squared using the n plus 1th terms of the sequence is the same thing as, on the right, x squared minus 2y squared using the nth terms of your sequence. So whatever terms of sequence, if you read along to the nth terms, you will always get x squared minus 2y squared being the same thing. I hope it's 1. Is it 1? Oh yeah, because I'm starting. They told me in the first part to start with numbers such that you get 1. That's why they told me to do that in the first part, so that I've got a sequence where x squared minus 2y squared starts as 1 and stays as 1. And we've proved in the first 2 parts that it stays as 1. And yes, I would describe this as comparing coefficients. If you call x squared, yeah. So technically it only has to hold for numbers that are in the sequence, but I think the only way that I know to think about this is to just think of it as coefficients of x squared and y squared and of xy, which is slightly overkill, but I think it's good. Okay, so what I would do for part 3 is generate the sequence. We've got rules now. In part 1 we have a starting place, and in part 2, together with our information about A's and B's, we've now got a rule for generating numbers in the sequence. And if you do that, then you can generate these massive numbers that give you these things. They're huge, so their ratio has to be about root 2. By which I mean, if you've got really enormous x squared minus 2 times enormous y, I'm even writing large, enormous y squared equal to 1, then this is large, and this is tiny. So crucial observation, these two behemoths have got to basically cancel out. They've got to be large, the same size, more or less, so that their cancellation leaves just a tiny remainder. This simplifies really nicely to say that x over y, if they're positive, they're both positive. So it's about root 2. So the sequence that you're generating is rational approximations to root 2. You find numbers like 99 over 70, which is about root 2. I just think that's neat. Good, right, that was 10 minutes or something. Repeat the explanation for 3, confused as to why you did it. What did I do? So for part 3, my idea is that I'm going to work out, I don't know, is that 5? Maybe it's 4 or 5 or something. x5 squared minus twice y5 squared is, using the previous part, x4 squared minus 2 times y4 squared, which is x3 squared minus 2y3 squared, and so on and so on and so on. I can, in part 2, the thing I love is part 2 you prove a fact, and in part 3 you get to use it. And the switching is using maybe different parts of your brain or something, or is using different ideas to say, well, algebraically you can check this is true, and then on a slightly more intellectual level you can do something with it. Say, aha! You told me to start off with this thing being 1, so x5 squared minus 2y5 squared will also be 1. And those numbers might be enormous. Excuse me. Right. How did I find the numbers for 3? Oh, for part 2, these 2 and 3, I found these numbers by comparing coefficients. On the left, I have some mad combination of xn squared and yn squared, and also these xn, yn things. I've just multiplied out the thing in the question, putting in n plus 1 and yn plus 1. It's really a horrible mess, and the question says that I'm supposed to get xn squared minus 2yn squared. So I'm comparing the mess on the left with 9xn squareds, and also minus 2 times a squared by xn squareds. And on the right, it's more of a calm thing. There's just one lot of xn squared. So I have equations like 9 minus 2a squared should be 1. This horrible mess that you get should be simple. Horrible mess on the left should be nice. Horrible mess for the xmyns, I have this idea that 24 xmyn minus 4ab from multiplying out, like the cross term in the middle. And I just want to see any of those. So I don't have any xmyns on the right, so I get these different equations. How would I get some numbers? Oh, so I'd actually calculate them, right? At the top of part 2, those are rules for calculating numbers. It tells me that x5 is 3 times x4 plus 4 times x4. 4 times y4, sorry. So to calculate x5 and y5, I need x4 and y4. To calculate those, I need x3 and y3. So I'd calculate both sequences together. So maybe you make a little table or something that goes when n is 0. Do we start from 0? I think we start from 1 in this question. And I would calculate both. So I've started from 1, 0, or maybe I started from 3, 2. And then the next thing I do is apparently 3 times this plus 4 times that, which is 9 plus 8 is 17. And the thing over there is a times this, wait a minute, a is 2. A times this is 6, plus 3 times that is another 6, is 12. So I get 17 and 12, and then I just will keep going. Work out the next ones, x3 and y3, and keep going, a little table. Yes, good. It always reduces down to being x1 squared minus y1 squared using this kind of chain of logic down here. It's brilliant, isn't it? So you can generate these huge numbers like 17 squared minus 17 squared minus 2 times 12 squared. Put this down here. And it really is true that 17 squared minus 2 times 12 squared, you don't, at any point in the question, you don't need to work out these numbers, but it really is true that this is 1. I just think that's neat. You get to find big square numbers that work in this linear equation. Who doesn't love big square numbers? So I think I'm claiming that 99 squared minus 2 times 70 squared is exactly 1. I don't even really know what 99 squared is. I guess 100 squared take away 100, take away 99 is 9801. I said I would be quick, and I'm not being that quick. The problem is that I really like this question. Yeah, so that's 1. Oh, I like it when you can check your answer. 99 squared is 9801. I should remember that. Sounds good. You know, not quite 10,000. Okay, whatever. It's good, isn't it? These are called Diophantine equations in general. That's a big class of problems. The one on the board, I think, is an example of something called Pell's equation. It's a thing. This is such a good math question that occasionally I've asked other people to write math questions and they have suggested almost exactly this question, not realizing that we've already done it. Yeah, if we hadn't done it in 2008, we really would have done it at some point since. It's just such a good idea for a question. You get massive squares that do a thing. Anyway, good. Right, we've got to move on though. We've got to do the other one. Ratio part at the end is just sort of fine. It's just sort of. I sometimes say rider for when you have like you need to imagine a large horse with a small person riding on top. And they're also here for the ride, right? You spend most of the question working on large horse with all this sort of stuff going on. And then at the end, there's just, hey, also here, and sort of thing riding along as well. Little bonus thing, which it is good because it demonstrates why you might care about this sequence and solutions to that equation. But yeah, anyway, why 1 anyway? Do you do other values? What other values can you put there? Which values are taken by this quadratic form? Tricky questions. Right. What do I see next? If I scroll, I will see hints, and then I'll see a question about SM, which lots of people wanted to do. So we're going to talk about it. This has also got some algebra and then some understanding of what the algebra is actually telling us. So I am going to try and skip some of the algebraic details. Let's see if I get away with that. The first 2 parts I think are quite technical. There's a lot to write down, which I could write on the screens or something. But I want to use the fact. So what I want, hopefully you've done parts 1 and 2, to just try what if, just imagine, what if 2 plus 8 plus 24 plus ... plus n 2 to the n was equal to, and it is really not obvious, I think, why it should be this. Question mark. What if it's this? is this? What would the consequences be? You need to be able to work out the first 3 terms. It is helpful that they've given us these first 3 terms at the front, but don't get confused. The first 3 values of S are not 2, 8, and 24. I'm afraid the first 3 values of S that you'll need to do the question are this. This is kind of horrible. It's this. The idea is that S is the sum of the terms. So although it looks like it should be 2, 8, and 24, it's actually 2, 10, and 34, which I think catches out a lot of people trying to do this question, that you're supposed to be adding these things together rather than finding a formula or something for the general term, which also, the general term has a formula like this with, oh gosh, A equals 1, B equals 0, C equals 0. So if you got 1, 0, 0, then it's probably because you put in 2, 8, and 24 instead of 2, 10, and 34. We've got to do a little bit more work with slightly different numbers. The question walks you through it to try and say, what if, so this would be, for when n is 1, this would be a plus b times 2 to the 1 plus c. This would be 2a plus b 2 to the 2 plus c, and this would be 4a. I confused myself there. 4a times 2 cubed plus c. And these are linear equations in a and b and c for the numbers 2, 10, and 34. So I'm going to put equals, 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 and put like a big, what if these were equal to those? We would have equations to solve. And part 2 is to kind of solve them, which is not much fun, but the sort of thing that I reckon you can do. And you end up with, so ... This is the bit I want to skip because it's not very fun to watch somebody else do it. A is 2, B is minus 2, and C equals 2. I have tried to explain the algebra a little bit in the solution on the MAT Live worksheet solution page. It's not very enlightening, I think, to look at somebody else doing this. K in chat would like to do matrix multiplication, which I think might actually be harder. I think with small numbers, I think I would just go for it. Maybe that's me being wrong. But my strategy for these, if they've all got plus C, is to look at the differences between them. What am I writing? I'm trying to write difference. Because the difference will cancel the C's, and I'll also do it on this pair, and then I'm bound to get 2 equations in A and B, and then I can relax. So my one idea, if you like, is take the difference of these equations to get 8 and 24. Oh gosh, if I take the difference, then I get the numbers back. I get this. The difference between these things. Should have thought of that. So if I take the difference, then I should get n2 to the n, or something. Okay. Something like that. For that last term that's being added. Yeah, I'm doing quite a complicated thing in terms of A, B, and C when I do that. Okay, not obvious. Good. And if I do that, then hopefully everything will cancel out. Don't forget the multiplying by 4 and the multiplying by 8 down here. And multiplying by 2 up there. There's a lot of things going on. Right, okay, so I would like to try and claim that as a result of the first 2 parts, with those values, as a result, which we'll need to use lots of times to do this last bit of the question over the next 10 minutes. Okay, then part 3 also gets you to check it. I don't remember that being there last time I looked at this question. It's sort of a little bit like proof by induction, isn't it? But you're not required to know proof by induction. So the question is, you may now assume. For that, I would check. So using the formula, we've checked it for the first 3, but they're asking us to check that if it's true that SK follows this rule with 2, minus 2, and 2, then adding on one more term to talk about SK plus 1 there in part 3. Just call it SK plus 1. What's changed? Well, we've just added another term. We've added a plus K plus 1, 2 to the K plus 1. So the only thing we've got to do is to check that our formula for SK, I haven't written it down yet, plus this extra term on the end really does give us the formula that we expect for K plus 1. If we do that, then everything's fine. And then we're allowed to assume it. So I'm going to jump down to this assuming bit. There's maybe some maths that I'm skipping here to talk about. Let's just write it all out. Let's just go for it. 2k minus 2 to the k. We're asked to check, a bit like we did a check earlier on, plus 2 plus extra term for sk plus 1 is equal to what we hope it's equal to. Oh my goodness, is that, I forgot minus 2 in there. Oh no, that's A, that's B. So what we're hoping for is that we get 2 times k plus 1 minus 2 to the k plus 1 plus c. The c doesn't change. We're hoping that it changes things to take us from this formula to this one with k plus 1s in it. And it does do that because these are almost exactly the same thing. Am I happy? I think I'm happy. This looks like, how many 2 to the k's is this? Another k plus 1s? Yeah, I think I'm happy. There's a factor of 2 in here, so this is k minus 1. Lots of 2 to the k hiding in here. And this is k plus 1, looks, lots of, sorry, to the k plus 1, 2 to the k plus 1. This is k plus 1, so I think this is going to be 2k. When you add them up, you're going to get 2k, lots of 2 to the k plus 1, and that is what you want. So it's kind of weird. The formula's a bit messy on both sides of the equation, but a bit of tidying and it should be alright. Okay. None of that's very fun. And there's one request for me to go back a step and talk about how to get A, B, and C, which is the one thing that I'm skipping. So I'm going to do it like this. So say, take the difference of these two equations, and you'll get, the C's will cancel, and instead of having 8 A's and 2 A's, you'll get 6 A's, and instead of having 4 A's and 2 A's, you'll have 4 B's and 2 B's, you'll have 2 B's, and the difference is 8. Take the difference over here, and you'll have, instead of 32 A's and 8 A's, you will have 24 A's, and instead of having 8 A's and 4 B's, you'll have 4 B's, and the difference on the other side is 24. So now we've got this sequence of, we've got this pair of simultaneous equations, and they're actually super nice, aren't they? I can double this one and subtract it from that to get 12a is equal to 24. I'm doubling this first one, so take off 16. And I haven't quite got the right answer, but I'm close. What have I got wrong? 8s and 2s is 6, 4 and 2 is 2, 16, 32, take away 8, really is 24, 8 take away 4 really is 4, double this one, 16, 8, yep, I'm out by something. I knew I shouldn't have done this. Some of those numbers are not right, never mind. Oh, this really was part 3. Oh, okay. So what am I doing? I'm checking the thing in the question which says if. Let's write out the if a bit more. So the thing in the question literally says, once you've got to sk, if, and I'll write out what sk means. No, that's not sk, that's a geometric sum that I've drawn out of my memory. So the question for part 3 says, show that if 2 plus 8 plus 24 plus k 2 to the k, if this is true, for some k greater than or equal to 1, then, so show that. Sometimes I hit a packet of Streamlab, which also slows down the pen, which is fun. Show that if this is true, for some k greater than or equal to 1, then plus k 2 to the k plus another term is equal to f of k plus 1. So that's what, if you replace in the sentence for part 3, in the sentence, if you replace sk with this, sk plus 1 with that, fk with this, and fk plus 1 with that, you lose any mystery from what's going on. You're being asked, if this mad sum is that, show that this sum is equal to this. And the proof is not too bad. The proof is to say all of that is the thing that you told me it was, but in the if section of this proof. And there's a new term, and then I've just got to rearrange this. So now maths happens. I'm going to do some maths That's a sort of fight cloud of all the maths happening, and it'll turn out to be exactly equal to the thing that I want it to be equal to. You have to go and do the maths fight yourself, right, to get this. You know where you're trying to get to, and you know what you've got. You just got to try and push it all together. Okay. Let's talk about 4, which is the hard bit. So 4 introduces some new sums. Find simplified expressions. And an option is to redo all of the stuff we've done so far, but I don't love that because I think it's a lot of work. Somebody in chat had a suggestion. I saw it and it's been buried in chat now, so if you want to post it again, then feel free to post it again. But there's some relationship between this, where the n's are now decreasing, compared to the sequence that we started with, which was Sn is 2 plus 8 plus 24 plus n 2 to the n. I think there's a relationship between these things. And I hope that we can try and find it. Can I spot it? So the trick is going to be finding some n 2 to the n in there somewhere. Has Jack got any ideas? It's kind of tricky. The trick is to split all of these brackets. You probably don't want to split all the brackets, but if you split all of them, then things are not too bad. So crucially, if I write out one more, I guess the question is, where's the 8? Where's the 24? So if I write out another term, in some sense, there's the 24. 8 and 3 is hiding in this bracket, and there's some n terms as well, but it's not too bad. Yes, and that 1 on the end, it's actually easier to understand what's going on if you write this as n minus 1. That's what it has to be in the pattern, right? The reason that this sequence has stopped is that we've hit n minus 1 in brackets like that. So that 1 in the question has been written in to show what's going on a little bit. If you do that and you split all the brackets apart, then you get, as if by magic, something like this, splitting all the brackets. I even split this last one apart, which is underlined in pink. Some terms involving n, where I noticed that the powers of 2 outside and multiplying them are going up in powers of 2, and underlined in green, which is a darker colour, I have some familiar things, 2, 8, 24, and then, okay, it's not quite the term I expected it to be at the end. This is S, not n, but Sn minus 1. So I've got 1 plus 2 plus 4 plus 8 plus dot 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 plus 2 to the n minus 1, lots of n in total, in pink, and I've got minus Sn minus 1 in green, which looks like magic, but is just recognizing that these things are powers of 2 multiplied by the counting numbers, which is what Sn is. Aha! How did I know this relationship? Because I know that math questions often link things back to the previous part when you see something new. Left to my own devices, I probably, for Tn, I probably would try and redo some of the maths from before, because I actually think that the calculation in parts 1, 2 and 3 is not that bad, and I sort of know it's going to work. It'll be something like this again, and I might have to fit all the numbers, use different values of a, b and c, but my suspicion is that that looks pretty much like the same as Sn, and in fact it is up to some sort of minus sign. I should simplify this answer a little bit, right? This is 2 to the n minus 1 times n minus Sn minus 1. Ooh, which reveals that. Ooh, no, this is fine. I was going to say, there's a last term in here as well. But there's a minus sign, which doesn't quite simplify any more than that. Okay. Oh no, it does. Huh. We know a formula for this. course. So we can use our formula to simplify. And we can plug in formula. You can go. Are we supposed to be just coming up with these ideas? Yeah, I think so. The idea here is multiply out some brackets, or if you prefer, redo the same algebra that we just did, but get different values of A, B, and C, which is a bit of a sort of Hail Mary guess that it's going to be the same shape of thing in the end, but yeah. UN is an example of definitely using the previous part. So UN, I think you can recognise what this has got to do with previous parts of the question. So in this case it's 1, 2, 3, and then the n is divided by 2 to the n. So at this point, if I'm honest, left to my own devices, without the help of chat, I would probably go and try something like, well, this looks like halving instead of doubling. So I might try an plus b 2 to the minus n plus c and see if that works. I think it does work. You know, because it's halving instead of 1 over 2 to the n instead of 2 to the n. Otherwise it's exactly the same as Sn. But there's an easier way to relate this to what we've already done with Sn and Tn. It comes from the idea that there's some relationship going on. Are there 2 different Jacobs? I've just realised there's 2 different Jacobs in chat. Spelt differently. I've been conflating the Jacobs. We've hit 7 o'clock. I think I'm running late. I think this question is just going to be like that for me. One way to get faster at this, which Ginger Biscuit in chat has spotted, is that this one, the n is over here on the right, which is back where it was for the Sn sum, which is why I'm thinking about the kind of maths we did with Sn. But, well, Tn was kind of backwards. It had the n minus 1, n minus 2 stuff going on, which means, to my horror, that if you take this term and divide it by 2 to the n, you get that term. And the same is true for the previous one. I'm working backwards, that un really is just Tn divided by 2 to the n, which I'm not sure I'd have spotted that. I think both parts, I'd have tried something like this, I'd have been happy that it worked, and I would have moved on. I don't think I would have spotted in the MAT 2016 that you could do this kind of clever tricks to reuse the previous sums. So this is Tn divided by 2 to the n, with the terms written the other way around. Perhaps for both of these, it's helpful to write down a general term. They haven't quite done that for Sn. They've given you the last term, but what you really want is a general term, so that you can practice, I don't know, writing down the general term of Tn and comparing. So if you know, if you're happy with this kind of notation, then maybe that makes it easier. I'm not sure. What do I have? K is 0 to n minus 1 of, yeah, so maybe just writing it out is handy, because then I'm forced to think about this being powers of 2 and n minus k, starting with 0 and ending with n minus 1. So maybe writing it in this kind of condensed format forces me to think about, what's going on with the sum. Can I explain it in this really compact format using sigma notation? If I do, then maybe I have the idea about multiplying out the brackets, because I notice perhaps that this is related to the sum of k 2 to the k, which I already had. So un is just, let's write out un then. A new idea, we're going to write out some big sums. So un, let's try and write down the general term, is in each case, so I guess this one starts from 1 to n, and it's 2 to the minus k times k. So for me, that's like, it's a minus sign instead of, it's powers of 1/2 instead of powers of 2, which Yeah, no one's going to like this. If you reverse the order of the sum, but people are not going to like me reversing the order of a sum, are they? That's not going to be a thing that people like. I don't get the feeling that people want to see this. So let j equal n minus k. Yeah, nobody wants to see this. This is not a helpful thing, right? So then un is the sum of j equals 0 to n, but backwards of n minus j, 2 to the minus j. Oh, 2 to the minus, no, careful. K is 2 to the j minus n? What's minus k? J minus n. Which is exactly the same as that one, but with j's instead of k's, and divided by 2 to the n, which is a constant thing to be dividing it by. So I've also reversed the order of summation. So the limits, I suppose you could add, if you really wanted to, you could add from n to 0, going down by 1 each time, but because that's how these sums work, right? Like as j gets larger, k gets smaller. I'm not sure anybody would do it like this, right? To spot that you can reverse the sum, and that switches this k to an n minus k. I think that one's harder to spot, having written it out with the sigma notation. Whereas I'm saying maybe you stand a chance of saying something's being divided by 2 to the n. What was it? N's being divided by 2 to the n. Division by powers of 2. Is my top limit supposed to be n minus 1? Yeah, probably is now. Thank you. Thank you, Vikram. Yeah, after my switch, because this k equals 1 is my stop. Down here, it's just off the screen. K equals 1 down here is a stopping when n minus 1 is j. J is n minus 1. Thank you. Yeah, so then it does match the Tn sum. Good. There's a suggestion in chat that I explain why, if you want to do this sum, this means 2 plus 2 plus 2 plus 2. I'm using j now. How many of them are there? Well, in the background you can't see it, but running through this, there's a counter that goes j is 1, j is 2, j is 3, j is 4, j is 5, j is 6, j is n. So there are n of them. This is 2n. If your sum is unusual, but if your thing that you're summing doesn't depend on the variable in the what's that called? The summation variable. If it doesn't depend on j, then you just get lots of copies of the thing, and you're still required to add them together, but I mean, you can't see any n stuff in there until you've added together n copies of it. That was a really vague thing to say, wasn't it? I was trying to say it doesn't depend on j, but of course it doesn't depend on j because, well, it never does. It never depends on j. J is just a counter while you're adding things together, which could give you lots of different terms, or it could give you the same term lots of times. Yeah, okay. And so summand is the name for that thing there in chat. Like integrand. I really need to get a dictionary, don't I? Lots of dictionary questions. Okay, final part of the question is the sum sk itself. Let's talk, because this is quite hard. I've got to use the formula, I think. We worked it out in a previous part of this question, so we might as well. I'm going to put big brackets around this to show that I'm summing all of this from k as 1 to n. So just to check, this means you plug in 1 and you get, well, the number 2, then you plug in 2 and you get the number 10, and then you plug in 3 and you get the number 34, these numbers from before. And this time we're adding those, so 2 plus 10 plus 34. And my goodness, you might expect that to be much worse, but actually you can split this up into 3 separate terms. I mean, there are at least 2 things inside these brackets, right? Let's do one of the splits first. So I think this term feels kind of separate from this term. This is the one I was just asked about, so this is just 2n, because there are n terms in this sum and they're all 2. This one is a bit harder. We need to split it again, don't we? Maybe, I mean, we could. two things in here. We could do some fun relabeling stuff, but I don't think people want that. There are these multiples of 2, which are quite nice. They just double all the terms, and doubling all the terms is the same thing as doubling the sum, or has the effect of doubling the sum, I should say. That's the smallest sigma I've drawn today. Sorry about that. These are all sigmas. Some here. If you like, I'm using the fact that if you need to sum a plus b, c plus d, then you can sum the a's and the c's first and subtract the b's and the d's. That works well for finite sums. And then, amazingly, you might expect this to be terrible, but this sum here is literally the thing we've been doing all the way through. Then that's just Sn. This says summing from 1 to n, 1 times 2 to the 1 plus 2 times 2 to the 2 plus 3 times 2 to the 3, but that's 2 plus 8 plus 24, the thing we've been working with. And this sum is just geometric. Minus 1 or minus 3? Always get that wrong. It starts at 2, so I need to subtract 2, 3. Trying to go too fast. I should use formula, shouldn't I? I should use the formula. There are n terms. I've been a bit lazy. I've tried to multiply by 2 and subtract 1 all at once. Don't try and multiply by 2 and subtract 1 all at once. You'll get the order wrong. So actually this works. We know the formula. We get to use the formula again. And then we'll simplify everything down. It's a bit mad, isn't it? You plug the formula in at the end of the question as well as at the start of the question. So you start by using the formula, and then you end by using the formula. Let's get that all on screen, there you go. So you start by using the formula, split it down into manageable chunks, recognise some of the sums, and use the factor with this other part. And then, amazingly, that's Sn again. So you can add these things together and you get a very similar formula as the final answer. It's different because it's got a plus linear term on the end instead of plus a constant, but it's pretty much the same shape. It's kind of weird to me that you can add these things and it doesn't grow much faster than the largest term. Maybe that's the punchline. The largest term in these sums is so large that when you add together all the terms, you pretty much just get the largest term. And then if you add together all of those, well, it was still the last one that really matters. Good, okay, cool. I'm not sure I can be more helpful than this. There's a formula that we're using and we're trying to focus on, I think the skill here that is really tough, spotting all this stuff in the middle, is the constant switching between a kind of raw algebraic sort of calculation mode where we have a formula for sk, so if need be we can just head down, just go and plug it in, break it down into different bits and think about it. Don't think about what any of the terms are, don't think about what it means, just go and calculate stuff, just go and do things. Do these operations like if all the terms are even, you can pull out a factor of 2. If the terms are all the sum of two things, you can sum them separately and everything's fine. Raw mechanical stuff versus having to stop and think of ideas. So kind of different parts of your brain, I think. For halfway through this question, I think it really annoys people. They've been in this kind of calculation mode. It annoys me. And then you see these new things, like Tn and Un. Who ordered these? What are these? I'm required to think about these new objects. And then they don't turn up in the rest of the questions. So that's a little bit irritating. But you think about Tn and Un and then just wanting to add together Sn's for the end of the question. So, good. Okay, that mode switching between do a calculation and think about what you've done is quite important, I think, for mathematicians. Quite often in learning about maths, you might need to really understand the kind of nuts and bolts of something to understand why it's true and what's going on, but then be able to compartmentalize that and say, right, all of that, we did all of this algebra at the top, so much algebra that I skipped some of it and then went back and got it wrong. All of that we compartmentalize down into just having this formula. so that later on we can just say, well, don't think about all the A's and B's and C's, don't look down, just use that result as the thing that we're trying to sum. We understand it now. We've got it down into a little capsule. This thing is called encapsulation. Encapsulation, that kind of puts something in a capsule. It's the idea that as well as trying really hard to learn something, understand something, that you can also compress it down to just a fact that you can then use later on. Possibly you use that fact to prove something else, and then you capsulate that as well. So you kind of build this mathematical theory. Later on, if you study maths at university, you build this mathematical theory by doing loads of work, really complicated, gorgeous thing that you then compress down in your head into a true fact that is just in your toolkit of true facts that you can now deploy whenever you learn these quite powerful things that you just understand why they're true, but also squash them together. That's a bit like, I imagine, mechanics. Mechanics on cars probably learn how cars work, but that's also quite separate from driving, where as well as knowing how a car works and how to take one apart and put it back together again, to also just be able to right, all of that effectively, I push the pedal and it goes. And the drive is to not think about all of the different gears and cogs and things moving around, but you push the pedal and it goes. So the sum of 2 to the k be 2 to the 2 to the n plus 1. There is a correction to my sum, perhaps. I think I was close. So the sum of 2 to the n plus 1 minus 2. Maybe. Why have I put 3? Is it because I'm doubling and subtracting 1 too much? Maybe it is 3. Yeah, I think it is 2. This thing in here. That's embarrassing, because that one is just a geometric sum, the one thing that we've been learning today. I'm just trying to get these powers of 2. Should we do it with the formula? So there are n terms. There's a big 2 up. There's a big 2 up front. There are first term. Looking at this, is 2 plus 4 plus all the way up to 2 to the n. The first term is 2. There are n terms. Outcome ratio is 2. So yeah, take it back. It was 2 to the 2n plus 1 minus 2. And then we'll multiply by 2. I don't know where my 3 came from. I'm sorry. Thank you, chat. You're anonymous for that, which is very kind. Right, okay. I think I'm running out of things to tell you about something. Let's go for final advice or ideas about math syllabus stuff. Revising A-level and revising math syllabus is kind of the same thing. If you're learning A-level in school, then probably at some point you're going to revise the material. Maybe you've had the experience today of seeing something that was new. And now you'll get that, I think, pleasant experience of, at some point in your life, learning that in a classroom in A-level or equivalent. I think that's a pleasant experience to see it, but to already know the punchline, already know where that's going, to be sort of one step ahead. And the reward for being one step ahead is that you've now unlocked the ability to do almost every past MAT question, which is where we're going next with the MAT Livestream. We're going to try and look at past papers based on feedback from current students who did the MAT Livestream before you. We've been running this since about 2020. Based on feedback from students, we're going to try and look at all of the past papers. We don't have time on the stream to do every past paper question. But after August, we're going to try and look at a lot of past paper questions. I've got some guidance in a few weeks' time. We'll do a special live stream to talk about how to use the past papers and what you should be aware of when you're looking at past papers. We'll do that in 3 weeks. I've got a bit of a break coming up after this one. Oh, look at all this. I want to look at this picture again. That's a good picture. Let's put that on screen. So in about 3 weeks, we'll do a look at some sort of techniques for using past papers. And then after August, hopefully you've had a chance during August to look at some past papers. and we'll try and bring it all together and do live streams where we're just looking at past papers and trying to focus on questions that people want to hear about. That's the plan for what's next. Good. So thanks Murray, thanks Jacob. My advice for what to do next is to revise this if you've learnt it for the first time today. Let's look back at all the way back up to the top. We're going to look at some past papers. You've got a bit of time to get ahead of me now, if you weren't ahead already. If you liked that 2008 question, you could go and look at the paper it comes from. The paper's on the MAT website. Okay, but I think I'll see you for the next session, which is weirdly, it's in 3 weeks' time. So I haven't prepared. How many hours is that? 504? Minus 2 for the stream and a half. So I think 501 and a half hours. Ages, right? 501 and a half hours. That sounds like loads. Fact check. Chat, is that right? 3424. Help. Yeah. That's loads of time. Brilliant. What am I going to do with 501 and a half hours? It's pretty good. Ginger wants book recommendation. So if you like equations with whole numbers, then you might like number theory, for which I recommend this book, which is a mostly blue website called Topology of Numbers. You can also download it as a PDF. It's a free book. It's called Topology of Numbers, and it's got lots more stuff for equations like that. So if you like the Pell equation, then you can find out lots more in this book called Topology of Numbers. Alan Hatcher, who has been cool and released their book for free. That's something you can see. Good. Okay, right. I'll see you in about 3 weeks' time. 501 and a half hours. Until then, have a nice summer. Have a bit of a break if you can, and maybe try some more MAT questions. We'll meet back here to talk about strategies and talk about how it's going. I'll see you then. Right. Bye everyone. Thanks to Georgina in chat as well. Well done. Okay. Right. Bye.